Trace in the guy and Kim.
Trace, 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 trace. Nuclear rules. The atomic number is the number of protons.
Trace in the guy and Kim. In today's episode, we'll be talking about the difference between fission and fusion. They sound the same, but in reality, they're very different. E equals mc squared, the famous equation. Binding energy, nuclear energy, all in today's episode. So let's get right to it. Now over to Timur with his new famous single, Fission v Fusion. Yo, Timur on the mic. About to drop some exposed plutonium. Two different categories of nuclear, all make the differences oh so clear. To start off, we got fission, a free neutron being the key to ignition. It results in energy emission in lighter products to unique additions. It's simple chain reaction occurs in the reactor core, the main contraption. A neutron splits a particle, releasing more neutrons, and this reaction goes on and on and on and on. If it creates exactly one neutron, call it critical. Because it continues steadily, the reaction is cyclical. Less than one neutron produced, subcritical. Eventually dies out because mass is indivisible. Combine subcritical masses to make it supercritical, and it results in something oh so cynical. Boom! Alright, now onto fusion. Let me help you rid of your confusion. A collision of two particles at really high speeds leads to the release of a ton of energy. It's as simple as shooting two particles at each other with enough force to bind together. In an instant, the binding energy is released, and as a result, the product's mass and atomic number have increased. The products and waste are barely radioactive. I'm telling you people, the benefits are massive. What if I told you the same process that powered our stars can one day be used to power our cars? There are just a few problems with it. The process can cost quite a bit, and it is incredibly hard to be contained. These are the barriers to our Earth having energy that is sustained. There are so many unanswered questions on the topic of fusion, so it's up to our generation to find the solutions.
Now that we've learned about fission and fusion, let's take a look at how nuclear bombs were used in World War II. Over to Sharon with our segment of Blast to the Past.
Thanks, Georgia. In today's Blast to the Past segment, we'll be talking about the famous equation E equals mc squared and binding energy. According to my history book, a long time ago, 1938 to be exact, in a land called Germany, two very smart chemists made a startling discovery. They were able to split a uranium atom, a process now known as fission. Since uranium had so many protons and neutrons, it could release tons of mass during the reaction, which in turn created tons of energy. The energy released in nuclear explosion was proportional to the binding energy of the molecules in the reaction. The binding energy equation is known as E equals mc squared, Einstein's famous mass energy equivalence principle. Einstein was afraid that the Germans would get a hold of this information, so he wrote a letter to FDR. The US government then developed the Manhattan Project, which tested two types of bombs in New Mexico. In the little boy gun type bomb, uranium was shot through a gun at a uranium target, causing a critical chain reaction. In the Fat Man explosion, plutonium is surrounded by high explosive force that inwardly crushes the plutonium. The way the atomic bombs work was that the heavy nucleus split smaller atoms and neutrons, causing an uncontrollable chain reaction that triggered massive explosions. Soon after, the US used these atomic bombs to quicken the end of World War II and the Japanese surrendered. That's all today for our history lesson. Now back to Trace in the studio.
Fascinating stuff, Sharon. Sure, nuclear energy made a difference in World War II, but how does it affect us now? Over to our corresponding field agent, Georgia, on the current events.
Thank you, Trace. This just in. With a clear need for alternative energy sources looming on the horizon due to a lack of non-renewable resources and the harm that comes with burning fossil fuels, fission and fusion present the best alternative options. Because of this, researchers are constantly running more and more tests on the two energy sources in order to elucidate any implications both fission and fusion have as alternative energy sources. Of the two options, fusion presents the best option. And the reasons for this seem very obvious. Its reactions don't emit harmful chemicals like the fission reactions. The only problem is, it's hard to harbor enough energy to cause the fusion reactions to take place. However, this problem is not insurmountable. In fact, it has already been done at JET, an experimental facility in the United Kingdom. Their achievement is quite astonishing, as they were able to generate 16 megawatts of fusion power, enough energy to supply 8,000 homes. This development serves as an impetus for fusion research in the future and around the globe. Right now, researchers are working on an experiment called ITER in the south of France. The experiment is designed to reach a self-sustaining fusion burn, and it is projected to be finished by 2030, meaning that soon enough you and I could be using nuclear chemistry to heat our food and turn on our lamps. Back to you, Trace.
Thanks, Georgia. That was excellent. And thank you guys for tuning in on this week's episode of Trace Him, the Guy and Kim.
Thank you to the following sources for providing research for tonight's episode. Without you, the production of the show would not be possible.